Okay, so in this video, I'm going to talk about the more calculus version of Faraday's law. So let me kind of start where the last video left off. So the non-calculus version, you can get an EMF that's every bit as real as the EMF from a battery, but it's not from a battery. This electricity is going to be driven by a changing magnetic flux. And the absolute value signs here are simply because we really only need this formula to supply the size of the EMF. The direction we're going to get from Lenz's law separately. This EMF drives induced current just like it would if it were from a battery. And we're going to get the direction of this induced current from Lenz's law. So this formula basically is just to get us a number for the EMF that we can work with, and we'll do some other stuff on the side separately. That's the non-calculus version, and for the calculus version, it's not actually going to be too much different. The official calc version, as you can probably guess by looking at this, this is just a thinly veiled derivative for anyone who doesn't know calculus. This would be, of course, intimidating, but you guys do. So essentially, the spirit is the same. If there's any change to the magnetic flux over time, that will drive an EMF. So the deltas have just turned into D's for this, of course, for infinitesimal changes. The one big difference, of course, you will notice is that the official version of of this law, if I can get this pen to work, does have a minus sign in the front. That minus sign is the mathematically sophisticated coding of Lenz's law. Essentially, if you're doing this very, very formally mathematically, that minus sign would make sure that the direction of the current is going to be trying to fight the change instead of being with the change. But I'll just tell you right now that in almost all cases, we're not going to try to do that so much either. So again, we're essentially going to ignore that minus sign. I think the one exception might be the electric generator. But any other time where, so just like later to put that in here, for the electric generator, we're going to keep that minus sign there. You'll see why. There's just a whole lot of changing flux, so we just have to do it a little more formally. But for now and for most examples, essentially you're going to kind of do the same thing that we're doing up here. We really only want a number for the EMF. We're going to just kind of take the absolute values there and not worry about it too much. And so, even if you take the derivative of some flux and you get a negative, just sort of ignore it. And you'll kind of see when I do some examples with this, you'll kind of see me do that and you'll kind of get a sense of how that all works. Now, let me remind you about flux. Now, we have studied flux all the way back in homework number 4. So this would be a good moment, if you don't remember at all what flux is, to go back and review. But remember that flux is a quantity that is often associated with field. It's essentially, if you have some sort of field, in this case magnetic field, and you sort of put something in there to catch it, okay? So some sort of surface area that's catching it. And let me remind you that if you're doing this, then the essence of flux, of course, you can have that the field is changing across the entire area, and then we have to use the fancy formula. So integral of B dot dA. And we never did that with Gauss's law in reality, so we're not going to do it again here either. We're just going to use good old B dot A. So we're going to assume that, which is B A a cosine of the angle between B and A. And so we're going to assume that the magnetic field has a nice relationship across the entire area with the magnetic field is uniform across the entire area and has a nice consistent relationship with the area vector. The area vector, just to remind you, we have a normal that points perpendicular to the entire area. And so, for instance, for this particular drawing, the angle between the normal vector and B is 0. So remember that the area vector is simply the area of the of this catcher, and then it's given its direction by the normal. So that's pretty much what we'll use. We'll use B dot A. Now, just as a reminder, there are, when you're working with open surfaces, so with open surfaces, then there will be an ambiguity in the normal. You could choose it this way as well. Sorry, that's almost the same color, so I should probably make that color different. So this is the other choice. For open surfaces, there is an ambiguity with the choice of the normal vector. And so there will be a sign ambiguity. If instead we chose that this was the normal, then the magnetic field and the normal are 180 degrees apart, and cosine of 0 is +1, but cosine of 180 is -1. So that does introduce an ambiguity of sign. With the one choice, it'd be +1 here. The other choice would be -1. Again, that's not really a big deal here because we don't really care about the signs. We're most likely going to knock it out anyway right here and not care about it. And so what I would say is just choose the normal such that you can just deal with positive quantities in any way. It's not going to hurt you if you choose the other way whatsoever. And later in the electric generator, the reason why we keep the sign is because we actually end up spinning this, and so we just have to pick one choice for normal, but then that normal is going to take turns being 0 and 180 degrees from the field anyway. So in that case, we just pick something, and then you're going to get a minus sign anyway. But that's getting a little ahead of myself. So that's how you compute flux. I mean, just as a reminder, we didn't have this ambiguity with Gauss's law because, of course, we had a closed surface. Now the surfaces have to be open. If you recall from the last homework, if your surface is closed, in other words, we're doing this over a closed surface, then the result is always going to be 0 anyway. This is the no magnetic monopoles rule. So Gauss's law, this is essentially Gauss's law for magnetism. And it's super boring because while you can have an isolated plus or minus charge, you cannot have an isolated north and south magnetic pole. So we would never do this over a closed surface, where, of course, with Gauss's law originally, it was that sort of resolved the ambiguity in the normal vector. So in this particular case, we're always working with open surfaces. There will be always that ambiguity in the normal, but that's not a big deal because we don't really care about the sign in most cases. Really the only difference so far with what we've talked about before for homework 4, of course, in homework 4 with Gauss's law, we always work with closed surfaces. Now we're working a lot more with open surfaces. And the other thing that we will wind up doing a lot in magnetism, so now we're catching magnetic field across our area instead of electric field. A lot of times, instead of just putting in one catcher, we'll put in a whole stack. So like say a whole bunch of wire coils or something like that. And in that case, if we're going to put in a bunch of these, let me draw in so they have a bunch of catchers kind of all stacked on top of each other. And we have n of them. For this particular scenario, we can just multiply the flux through 1 by n, so it'd be like that. So our final flux formula that we are going to work with, NB dot A, looks a little tiny bit different from what we saw before, simply because we might have a number of different catchers instead of just one. And of course, the magnetic field is now what we're calculating, the flux of magnetic flux, not the electric flux. So let me go ahead and take this onto a new page. That was kind of just a little bit of a summary of flux. So here is the formula for Faraday's law, and the flux calculation is going to be N B dot A, or if you want to write it out, N B A cosine of the angle between B and A. And so let me point out all the different options. As long as the flux is changing with time, something in the flux is changing with time, you'll get an EMF. There's many ways to do this. In fact, there's 1, 2, 3, 4 different ingredients in this formula. So you could have a change with time of N, B, A, and or theta. And all of those things, if any of those change with time, you will get an EMF. And if there is a path for current to flow, you will get an I induced. Okay? And so that actually gives us many different ways to generate an EMF. And what we're going to actually do is going to take a look at each of these with time. And when we're done doing that, that's actually going to be the end of what is covered on this homework usually. The first is magnetic field itself. So if we have a magnetic field itself changing with time, that will lead to a flux change with time, and that will lead to an EMF. And that is going to be my first example that I do, the magnetic field itself changing with time. The second possibility would be the area of the catcher actually changes with time. So if you have a change in area with time, so it's not that the field itself is changing, but the reason your flux is changing is because this catcher itself is changing. So you're catching more or less flux with time. So you're sort of evolving the shape of the catcher. So that will also lead to a change in flux with time and an EMF. That's my second example. This is what's sometimes known as motional EMF, okay? Because you are actually causing the flux change by some sort of actual physical motion of the thing that's catching the loop. So that'll be my next example after that. My third example will be when you actually change the area, the theta itself. So d theta, some sort of angle change, okay? And that again will lead to a flux change and lead to an EMF. So what you do for that is that the catcher, you will actually twist it, you will rotate it within the magnetic field, and so the normal will change its angle relative to the field, and you'll catch more or less flux with there. And this is called this will be the electric generator, and that'll be the example next. And then the final example has something to do with N, the number of loops. Now, I'm not actually going to change the number of loops with time, but it turns out, so this one you have to take a little bit more loosely, but there's something I can do with the number of loops that's at least interesting. So I'm not going to change the number of loops with time, but there is something interesting I can do with that, and that is what we call electric transformer. So sometimes that ends up being on a new homework, and sometimes it ends up being on the same homework. So just remember that depending on the particular semester, this topic may or may not be on the same homework, or maybe bumped to the next homework, just to keep this this first main homework on Faraday's law, you know, to a particular length or whatever. So essentially, and of course, I should point out, you could change more than one at a time, and those would definitely change the flux potentially. I'm not going to do that to you, so it's going to be one of these only. So it's going to be something with n, b, a, or theta, not more than one. Although, of course, if you did have to change more than one, essentially you just go in here. This just goes in here, and you could do the product rule here. If more than one of these things was changing the derivative, you guys know the product rule for handling that. So I'm not going to do that, but the way you'd handle that is as far as at least the math is concerned, would be something you guys could definitely do. So these will be the 4 examples that I do. But before I do that, there is also one other thing that I need to address with Faraday's law that is not contained in the earlier version. We, of course, saw earlier in the course, this is homeworks 3 and 4 mainly, that, of course, there is a relationship between electric field and voltage, right? So these are just 2 different pictures of seeing what's going on in empty space. Electric field is the proxy for force, and voltage is the proxy for energy. This is just force per charge, and this is potential energy per charge, right? So you might ask, okay, here's an EMF. That's just a fancy variable for voltage, right? It's going to turn out that it's actually a little more complicated than that now. In homeworks 3 and 4, we sort of, these are all just regular old voltages. We might reserve this EMF character if it's the voltage of a battery or something like that, but there was no difference. We're actually going to see now that there is a little bit of a difference. There, you might ask, is there a corresponding electric field to this? Yes, there is. Is this EMF the same as voltage now? Not quite. So let me do a little bit of addition to this. There is the correspondence here between electric field, induced electric field, and EMF. This is a kind of a little bit of a interesting relationship. So there's electric relationship between E induced and EMF. This, I guess, this is homework to, usually homework 10. And if you have more homeworks than that, then it might be included. So for instance, if you end up having a homework 11, then it continues on to that. But let's talk about what's going on here with these guys. There's a lot to unpack. I'm just going to give the basics in this video, enough to kind of do the homework and mostly, and then I'll give an optional video to just kind of delve more into this relationship that's more intended if you plan to see this stuff in the future, that you're a little more prepared. But let me essentially talk about this a little bit. Okay, so let's say you have a situation, you have some sort of, we looked at the Lenz's law stuff already, so we kind of understand the concepts of this. So let's say you had a conducting ring, and you're waving a magnet nearby it, changing the flux, and you have these, of course, these positive charge carriers inside this conducting ring that are just sitting there. These are all pluses if you can't see it very well. And they suddenly pick themselves up from rest and start flowing in a current. And we can get the direction of that current with Lenz's law. So let's say they all start flowing like that. And of course, the current that you would get, well, you would just get it from Ohm's law. So that would be the induced EMF over R. Well, of course, we learned already, starting with homework 8, that a magnetic field is not going to be able to pick up charges from rest. It's a deflective only, right? So we learned that magnetic force is deflective only. So the only thing that could pick up these charges from rest is an electric field. So what's the direction of that electric field? The direction of that electric field, well, we also know all the way back from homework 1 that positive charges, if they're going to start from rest and just start moving in a particular direction, positive charges follow the direction of the electric field. So what that must mean is that the electric field is actually pointed this way. So that's the E induced. So essentially, the rule here is that E induced, okay, first of all, it's needed whenever from your perspective, that the charges started from rest. The only thing that can pick up charges from rest is an induced electric field. And the induced electric field points the same way as the induced current flows, right? Current's made out of positive charges, so whichever way they want to go, well, positive charges also want to flow downstream to the induced electric field. The relationship here, you can see the E induced does form a closed circle, right? If these charges are flowing around in a circle, then the E induced is pointed that same way. So this line integral, it looks exactly the same as Ampere's law. In fact, it works exactly the same way. This ends up being just E induced times integral of dl, which is just L, and the length around is just 2 pi r. So in essence, if you want to get E induced, the induced electric field, you just take the EMF that you've already found and divide by 2 pi r. So I guess I can even just write that here. It's like that. And I think that'll get you through the entirety of what is being asked in these homeworks. And what is r? I guess I should say r is just the radius that you're working on. So you're doing a line integral around wherever the current's flowing, and E induced is doing the pushing. Now, I'm gonna, like I said, I'll leave the nuts and bolts a little bit or the deep dive into this relationship to another video that is not to clutter up this one, but you can sort of smell that there's something suspicious here. This is the first time we've seen an electric field that actually forms a closed loop. The current just keeps going around like this. Like we learned, for instance, that in homeworks 3 and 4, that the electric field always points towards lower voltage. Okay, so it points from, if you have like 9 volts over here and 8 volts over here, the electric field points the way. Okay, so we have a closed circle. Okay, okay, where's the lowest voltage on this? Okay, so if this is 9 volts, 8 volts, 7 volts, 6 volts, 5 volts, wait, but this forms a closed circle. How does that work? That doesn't even make sense, right? The moment your electric field forms a closed circle, there is no lowest point on that circle anymore, okay? Well, the whole scheme falls apart because over here, this was what is a conservative force, okay? And potential energy makes sense for that. And you, of course, like learned in Physics 1 already, like force of gravity, force of a spring, there's associated potential energy to that. This is now generating, you can still say this is force per charge, but this force is now what we call a non-conservative force, like you learned in Physics 1, friction or something like that. There is no associated potential energy. It just doesn't make any sense. And if there's no associated potential energy, like there's no potential energy of friction, right, then the whole concept of potential energy per charge doesn't make sense. And so here, we don't use the character V. V is sort of reserved for potential energy per charge. What we use is we use EMF when, not just when we want to be fancy and it's the voltage of a battery, but EMF is actually when we use when we are dealing with a non-conservative electric field and we don't want to use V here, so we use EMF. It's not potential energy per charge. It has to do with the energy it still has to do with energy per charge, but it's not potential energy anymore. So what you can see is here is that every push around that the charges get as they go around this circle, the energy keeps on being added to them. If there were no if there were nothing in their way, they would keep going faster and faster and faster and faster and faster and faster. Of course, in this particular case, they are not getting faster. It's just that that energy is being bled out as heat. So every revolution, these charges are letting out their energy to heat. Where do they get more energy? They, of course, keep getting pushed by the electric field. Anyway, I don't want to get too much into the weeds on this video. That was just a quick blurb about it. But as far as when you're asked for the induced electric field, just as a summary, remember, you only need to invoke it when these charges, from your perspective, just pick up and go from rest and form into an induced current. If that's the case, then the induced electric field points the same way as the current flows. And then to get the number for it, divide the induced EMF, which you got from over here, and divide it by 2 pi r, where r is the radius at which this is happening. And so you could kind of think of that as a sort of a sideshow. Most of the time, we're interested in finding out the magnetic flux. It changes. Why does it change? It changes because something's going on with one of the parts of the flux, many different options. And if some part of the flux is changing, again, remember, changing with time is important, we will get an EMF, and that's kind of the heart of this. The heart of this being that an EMF will drive a current according to Ohm's law. From here, we have the calculus version. Your starting point for all these calculations, just to kind of put it all here as a summary, we got that. Again, most of the time you're going to ignore that sign, mostly, except for the electric generator. This usually ends up being like this, like so. This you can use for Ohm's law. Lenz's law gets us the direction of the induced current, and the flux itself we're going to calculate with NB dot A, so that we can get more flux usually, because we have oftentimes have more than one catcher. So that essentially is kind of the master cheat sheet which we are going to use for this law. And then remember that if N, B, A, or theta change with time, we get some sort of EMF. And again, if you're going to have not only EMF but current, you better have a resistance that isn't infinite or something like that, because otherwise you can't get any current that flows, or not much. So that right there is the essence of the law. And then what we're just going to do is going to go through these examples, and that's going to be the Faraday's law problems here in a nutshell.